Hello everyone. Today we will see how to find degrees of freedom. It is also known as degrees of kinematical indeterminacy. So we have a different structure. We have a simple pin jointed frame, It is also called as truss, and we have rigid jointed frame, rigid jointed frame. So in this video we will see how to find degrees of freedom for truss and for rigid jointed frame. So the degrees of freedom is denoted by dk. Okay, so first we will see truss element. We will see how the formula is developed. I will take a simple truss example. This is a very simple truss. If I take any joint of the truss, so this joint has got two displacement, delta x and delta y. We are not calculating rotation in truss, we are only calculating the deflection in x direction, deflection in y direction. So theta is not a predominant factor here, so we are not calculating theta. So each joint has got two independent displacement component. Each joint of the truss is having two independent displacement component, delta x and delta y. Okay, so we will see how to find a dk. You have to go to each joint and you need to define the displacement of each joint. At this joint you do not have any reaction, so this joint possibly it will deflect in vertical direction, it will also deflect in horizontal direction. So at this particular joint the degrees of freedom are 2 in number. Come to this joint. Here you have got vertical reaction, means there is no vertical deflection because vertical reaction will resist the vertical deflection. At hinge support you also have horizontal reaction. So when you have horizontal reaction, there is no deflection in the horizontal direction. So here deflection in vertical direction and deflection in horizontal direction is not possible because of the reaction component in the both the direction. Here we have a roller support. In roller support the reaction is perpendicular to the support. So here we have reaction in vertical direction, so there is no vertical deflection, but this has no horizontal reaction. There is no horizontal reaction, means it will have horizontal deflection. Once again, here we don't have any reaction in vertical direction and horizontal direction, so that is why we are getting two displacement component. Here we have reaction in both direction, so that is why no displacement in vertical and horizontal direction. Here we have reaction in the vertical direction but no reaction in the horizontal direction, that is why the displacement is there in the horizontal direction. So here for this structure dk equals to 0, 3 in number. Degree of kinematical indeterminacy for this simple truss is 3. We can develop the formula by following the same concept, dk. Now I told you each joint has got two independent displacement component. Okay, so J is number of joint and each joint has got two independent displacement component, delta x and delta y. And you see in the problem we have seen there is resistance to the displacement. Which component is resisting the displacement? The reaction, minus R, because here there is no displacement, just because here you have the reaction. Reaction is a component which is resisting the displacement. So here R is number of reactions. Now we will use this formula to find the decay for this simple truss. Decay equals to, see, you just have to count the number of joint and number of reactions. You can directly use this formula. Whichever truss you want to solve, you can directly use this formula. You just have to count the number of joint and number of reactions offered by the support. You see how many joints we have? 1, 2, 3. 2 into 3. And how many reactions? Here 2 reactions, horizontal, vertical. Here only 1 reaction, minus 3. So decay equal to 3. We will see simple example. These are the different simple pin jointed frame. We can use directly the formula. I have derived the formula. Decay equals to 2j minus r. Just have to count the number of joint and number of reactions. So here decay will be equals to 2 into 5 minus 5. Decay equals to 5. You can also go to each and every joint in the truss element to define the degrees of freedom of the structure. Here at this joint, you have two reactions. It is a hinge support, vertical reaction as well as horizontal reactions. So there is no possibility of deflection in both direction. Here also the same case. At this point you don't have any reaction, so there is a possibility of vertical deformation and horizontal deformation. Here it is 2 in number. Here also don't have any reaction, same thing, 2. At this joint you have only one reaction, so there is no possibility of deflection in vertical direction, but this will deflect in the horizontal direction. So anyhow you are getting the same. You are getting the same by using the formula or by going to each and every joint defining the degrees of freedom. Here you can count the number of joint, 1, 2, 3, 4. This is not a joint, just a member are crossing each other. This is not a joint. So here joints are 4. Reactions you can calculate. Here 2, here 1, R equals to 3. So decay equal to 2 into 4 minus 3. Eight minus 3 equal to 5. Here also you are getting 5. You can go to joint. Here no deformation. Here 2 deformation. Here also 2 deformation. Here only 1 deformation. Come to this truss. Here no deformation. Here only 1 deformation. Here 2 deformation. Here also it is 2 deformation. So decay for this structure is 5. Now we will see how to find degrees of freedom for a rigid jointed frame. You take any joint of a rigid jointed frame and you can define three independent displacement component. Take any joint here. This joint, possibly it can deflect in horizontal direction, it can also deflect in vertical direction, and there is also a possibility of rotation. So each joint has got three independent displacement component. Three independent displacement component. Okay, so it depends upon the reaction also. Now we will go to each and every joint and define the degrees of freedom. At this joint there is a fixed support. So at fixed support you have three reactions: vertical reaction, horizontal reaction, and a resisting moment. You have vertical reaction, you have a horizontal reaction, and also resisting moment. Vertical reaction will not allow vertical deflection. Horizontal reaction will not allow horizontal deflection, and the resisting moment will not allow the rotation. So the deformation of this joint is 0. Next come to this joint. Here there is no reaction. It can deform in vertical direction, also in horizontal direction. In this joint may have the rotation. So we have to define the possible displacement of a joint. Here also the same case, vertical rotation and horizontal deformation. Here 0. So decay for this structure is 6. We can have the formula: dk equals to, each joint has got three independent displacement component, and those displacement is resisted by the reaction. So R is number of reaction. dk equals to, count the number of joint. Here the number of joint are 4. 3 into 4 minus number of reactions, 3 plus 3, 6. So you will get 6. But most of the time we cannot use this formula, most of the time, because we have to neglect the axial deformation. Axial deformation of column, and we have to consider the compatibility okay, sorry, we have to consider the compatibility of the structure. So this condition is called inextensibility. Inextensibility of column and inextensibility of beam. With regards to inextensibility of column, we have to neglect the axial deformation of the column. Whatever the deformations are there of column in axial direction, we have to neglect. Okay, this axial deformation, neglecting of axial deformation is with respect to inextensibility of column, or axial deformation of column are neglected. So now we will see the inextensibility of beam. Inextensibility of beam means we need to consider the compatibility of the structure. Compatibility means the structure should stay together, the structure should move together. Means if I draw once again, horizontal deformation of this joint and horizontal deformation of this joint should be same, like this. If the structure is deforming, it should deform together, means structure should stay together and structure should move together. So this delta and this delta should be same. in order to have the compatibility of the structure. Okay, so now again we need to define the decay of the frame by considering the inextensibility condition. Here we have neglected the axial deformation of the column vertically. Okay, now this joint will deform. This deformation and this deformation both are same. Instead of showing two deformation, you just show only one deformation, because this delta, this deformation and this deformation both are same. Instead of showing deformation in both joint, you only show at this joint. This will suffice. Okay, so you have neglected vertical deformation of column, axial deformation of column, and you have taken only one lateral deflection. You are not taking here. Okay, so this thing we need to consider. This will rotate and this will also rotate. So here dk equals to 3. Always what we have to do in case of rigid jointed frame, we have to go to each and every joint and define the decay. You don't have to use this formula. This formula will not consider the inextensibility condition. We will see how to find the decay here. Here there is no deformation, vertical, horizontal and also the rotation. Here this joint will rotate and there will be a horizontal deformation. We are neglecting the axial deformation of the column. Here the joint will rotate and we don't have to show the horizontal deformation, because the horizontal deformation of this joint and this joint both are same. So we have already shown here. We don't have to show here. Now what we have to do when you have a hybrid structure? Hybrid structure means some joints will be rigid joint and some will be pinned joint, or the joint will be an internal hinge. So what we have to do here? This internal hinge will separate this member and this member. I will name the member A, B, C, D. So there will not be any joint rotation. This member will rotate independently, this member will rotate independently. This internal hinge will separate CB and CD, so that CB will have its rotation and CD will have its rotation. Okay, so again here it is 0, one horizontal deformation and joint rotation. Decay for this structure is 3 and here decay is 4 because of internal hinge. So we will see for this structure how to find decay. Here we have 3 reactions. There is no displacement in any direction. Here we will have a joint rotation and one horizontal deformation. Here also we will have a joint rotation. We don't have to show the horizontal deformation. Here also we will have a joint rotation. Here joint rotation and one horizontal deformation. Here we will have a joint rotation. You see, two members are connected to the internal hinge. So this member will have its rotation, this member will have its rotation, because the internal hinge is separating the member, so that the member will have their rotation. There is no joint rotation, there is the member rotation. Okay. With at support we have to see with respect to the reaction. Here we have vertical reaction, horizontal reaction and a moment. So no deflection in vertical direction, no deflection in horizontal direction and no rotation. Here the moment is 0, the resisting moment is 0. So this support, it may rotate, it can rotate because the resisting moment is 0. So at support we have to see with respect to the reactions. Here it is fixed, deformation is 0. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. dk equals to 9.